Hi, everybody. Thank you so much for attending today. Sorry for the technical blitz, but we're doing fine now. I'm Hope Butterbush, and I'm pleased to introduce you to our speaker today. Usually, a person who introduces a speaker and gives a lot of background information on that speaker. However, today I'm going to modify that, keep it real short, and just tell you how I know David. David and I met in 1991 when we both worked at the U.S. Department of Energy in Largo, Florida. David was an engineer working on federal contracts, and I was an educator placed in industry by St. Petersburg College to coordinate training programs. In 1995, David moved over to the University of South Florida College of Marine Sciences Center for Ocean Technology. I returned to St. Petersburg College. But in 1996, I was hired at USF College of Marine Science to work with scientific faculty like David. We worked together there for about 12 years, developing educational programs and grant proposals. And after I left USF, David and I continued to work together. I was part time, mostly volunteer, helping David with grant funding and researching background information for proposals and white papers. And during COVID, he and his wife, Carolyn, hired me again to work with them, and I've been working with them ever since part time. David and I had a project about 2 years ago in Second Life called Bayou Tahar. It was a citizen science project where we created a digital twin of the real Bayou Tahar that's located in Pensacola, Florida. That showcased David's Intelligent Waterways project. David's going to tell you a whole lot more about his background and in his incredible work as he presents to you the automation of science from human discovery to machine-driven knowledge. And now, take it away, David.
Yeah, my name is David Freeze. The title of my talk is Automation of Science, from Human Discovery to Machine-Driven Knowledge. I'm with Guided Particle Systems, and I'm also affiliated with Pensacola State College and the Institute for Human Machine Cognition. I'm an interdisciplinary research scientist, both in chemistry, physics, and electronic systems, my focal areas. I have 20 years of experience at USF in ocean sciences and engineering and also arts. I've published multiple works in different fields of oceanography, chemistry, biotechnology, manufacturing, electronics, and so on. I'm also a serial junkie. I have a company now and have had a series of companies over time. My primary research areas are looking at and exploring spaces using machines and technology. That's physical space, chemical space, and information space. I focus some work also on microsystems and embedded systems development. I primarily also work in robotics and automation for field sensing applications, and I constantly do advanced sensor development, chemical, physical, and biological sensors, and also focus on manufacturing technology development. I've started this talk with this saying, our view of the environment is dependent on our devices, and our limits in our analytical measurements leads to our partial blindness. What we humans view as is a slice of reality. The new horizon has machines that can work in collaboration and autonomously and explore these new spaces. So why is science changing? It's partly a scale problem. Modern science faces combinatorial explosion of different topics and the interaction of topics. Human-only experimentation cannot search these spaces, these topics efficiently. Data volumes now exceed human cognitive bandwidth. 2, instrumentation and data factories. Labs have become automated measurement systems. Sensor sequencing and imaging generates continuous high-dimensional data. Compute is now as essential as wetware or humans. Theory is no longer enough. Many systems are nonlinear, stochastic, and multi-scale. The closed form models fail. Discovery shifts from derivation to exploration. A fourth one is AI changes in the scientific loop. Hypothesis into experiments and analysis becomes closed loop automation. AI proposes experiments, controls instruments, interprets results. This enables 24/7 discovery at machine timescales. There's the economics of truth, slower science being outpaced by competitors, which drives more competition, more uptake in innovation and science, and you see automation starts to emerge. Automation lowers the cost per discovery, and competitive pressures force methodological changes. So this is a fifth factor, and the sixth factor is from craftsmen, the systems designers. So scientists evolved from hands-on operators to architects of discovery systems. The focus is shifted to objectives, constraints, and validation. So take-home point is that science is changing because the frontiers move faster than humans alone can follow. An optional perspective is automation of science equals the scaling of curiosity. That's the way industry scaled manufacturing. So what is the automation of science? Automation of science is systematic delegation of the scientific discovery loop. Question, hypothesis, experiment, analysis, and decision from humans to integrated computational and physical systems with humans setting goals, constraints, and meaning. So what is being automated? So experiment design and prioritization, instrumentation control, data analysis, model fitting, and pattern discovery, iterative decision making. These are all in a start to link together and can be done by machines. Not automated is a choice of objectives and values, interpretation in social and other contexts, and responsibilities, validation, and final judgment. That still is human dimensions, human domain. How it works. AI models propose hypotheses. Robotic software agents can execute them. Learning algorithms update the beliefs. In real time, the loop runs continuously faster than human cadence. What makes it different from traditional science is that we now have machines in the loop, closed loop discovery, and algorithmic exploration. And why this all matters is automation of science is not about replacing scientists, it is about scaling curiosity beyond the human limits. Think of it as moving from handcraft experiments to industrialized discovery. So up to this point, I want to be very clear about something. Automation in science did not arrive all at once. What most people think of an automated science is assistant science. Tools that help us do what we already decided to do faster or at larger scale. The real change happens when we move from humans in a loop to machines in the loop systems. In a traditional workflow, humans decide what experiments to run, machines execute them, and then everything waits while we think. In a closed loop system, that pause disappears. Data flows directly into models. Models propose the next experiment. Experiments update the models automatically. The critical shift here is not speeding, it's continuity. Discovery becomes a process that runs even when we stop paying attention. That's what makes autonomy qualitatively different from instrumentation. No, this isn't speculative. These systems already exist, unevenly, imperfectly, but unmistakably. In material science and chemistry, closed loop platforms are mapping composition spaces no one would attempt manually. In biology and drug discovery, adaptive screening systems don't just test compounds, they revise hypotheses in real time. In physics and engineering, We're seeing design space exploration replace analytical tractability, not because the theory failed, but because theory cannot cover the space anymore. What ties these fields together is not a shared technique, but a shared pressure. The search space outgrew human cognition. Automation works best where intuition stops being reliable. Now I put up this slide because this is a slide I used to present to all my earlier, work, and and this is in the early 2000s. So this is about a generational swing in terms of the automation and the direction. But basically, field sensors, field robotics, automation, and mobility were a contrasting and ongoing theme in my work. And it just shows you that I started doing this years ago and continue to do it. So this slide's presented to just show you the type of work I've done. This is on ocean platforms, marine robotics and ocean exploration platforms. To the left is just the general segments of developments on planning, navigation controls, fusing that into a system, and then being able to then have that system generate data and visualize that data. So to the upper right is a submarine that was used with a sensor I developed. That was one development, and then to the left is a surface vehicle, someone else's vehicle, but I've worked with them, and then we placed that together, and we created a greater capability. We had sensors on there and mapping out chemistry, and then the lower is a sensor or platform, mobile platform with sensors that it's a solar AUV, and that's a separate technology I progressed. So I just want to give you a kind of a slice of some of the things I've been involved with. So this slide is just to show the solar AUV in this case, which was on the previous slide. It can go for a long time in the water and have it stays at the surface. It can go subsurface and move through three-dimensional space. It's it's it, it's using solar energy as its source, and hence you can get a large. This this just shows the other vessel whirling around and doing work. We get highlighted in the news. Um, it just is a new capability, and once you bundle it with sensors, which in this case it was, it allows you to start mapping and creating more of that larger picture, and then the data that comes from that goes into visualization. So the primary drivers on these systems is that autonomous machines, ocean machines in this case, really provide a lot of capability. You can have inner space automated systems, in other words, being able to allow us to extend the human radius, the human scientists. So that's what already we've been doing, automating R&D science, automating monitoring, oil and gas automation, future transport systems automation. And so these areas are really compelling reasons why you would want to do this, especially when you go into areas where humans don't naturally exist. So beyond the motion of the platforms and these autonomous or robotic systems being able to move around, we actually want them to do things. And one of the things is I developed was a mass spectrometer. And this allows it to do chemical space and explore the chemical space out in the real world. And so I just want to highlight that with this slide. This is something that we have, and I won't go into it, but there's a chemical sensor that's got some real analytical power. So with that sensor and that motion platform, now you have the ability to start doing new ways of doing science. And so why do we want to use mass spectrometry and And the reason is for chemical exploration knowledge, or chemical space exploration knowledge. So in order to get greater penetration in the problems, you can use the mass spec and the motion platform to be able to, explore chemical space. This includes understanding environmental sources, pathways, dynamics, and fate of chemical pollutants, environmental and biomonitoring studies. Um, you can do environmental contaminants, examine bioaccumulation, food chain transfer, human and wildlife exposure assessments. Um, and the current studies I'm particularly focused on is current studies of emerging environmental contaminants for characterizing human and wildlife exposure pathways. This is just additional information as to why you would want mass spectrometry. There's quite a number of applications: pollution monitoring, um, chemical source material discovery, oil leaks, um, advection, diffusion studies, point source field profiling, shipping channel monitoring, mapping of oil spills, pharmaceuticals and environment, which is my particular focus right now. And just in general, this is about chemical ecology and how um, material flows through the ecological landscape. And and so in the robot plus the sensor, now you have the ability to be able to do chemistry and spatially distribute the sensing. So you can, with that, you can establish background levels of hazardous compounds, characterize natural hydrocarbon seeps and see where they go, detect elevated concentrations of leaking chemicals. These are all very important things. If you have suspected leaks, the ability to be able to do ROV or AUV surveys and real-time feedback for fine sourcing. It's called source localization. These are all possible once you have mobile platform with sensor and be able to then deploy them in the environment. This is just a picture, a cartoon of the overall process. All you need to know on this is just generally we keep the mass spec, which has a vacuum in it, which, it's a vacuum science technique, is on one side. There's a membrane that's specially tuned that allows the water, the ocean, to be on the other side. It allows permeation of chemistry through the membrane. And we can tune the membrane. Once that gets into the vacuum, this this vapor pressure gets ionized, the mass spec, the mass filter, analyze it. You have a detector, then it does its electronic detection, and then you create a mass scan from it. This is our version of the mass spec. It's got vacuum housings, electronics, and so on. It's the specification dimensions are on the left. But it's a very compact system and it's very powerful. So, and it's been operating up in 2,000 meters of crushing pressures. There's a second version we demonstrated. This is an ion trap, and it has more analytical capability. It's more pregnant. It has had some more bells and whistles on it, but it's generally you can get up to a greater range in atomic units, and it allows you to do mass spec. There's analytical techniques on that, but just so there's a couple of versions of mass spec we can use and have used on autonomous vehicles. So this is a composite image of the mass spec in a vehicle, and with control loops, you can then have it go out and effectively map out an area and get critical information. And this is what's been done on multiple occasions with the mass spec. But just goes to show you now, we've got the systems be able to then start to go into the automated exploration, automated mapping, automated loop. And that now we're we got the basis for being able to do automation in science. Here's a list of compounds amenable to mass spec, and some demonstrated analytical performance figures. In MIMS, you can do full scans or selected ion monitoring, either one. So it's basically show you you can actually do real chemistry of different chemicals and be able to then do analytical investigations with this. Here's some field data from use of the mass spec for ecosystems characterization. This is work of Tim Short and some collaborators in Southern California. Surface tows were effective in being able to drag the mass spec and be able to do hydrocarbon monitoring. But that work also, that hydrocarbon monitoring also then it's allowed us to start thinking of greater realms. And so one of the greater realms is oil and gas applications. I won't go through all of this, but you can see there's quite a number of subjects there that the oil and gas industry would use this and this technology for their operations and exploration. And so from that, we're able to then, which we did, start to engage with the oil and gas industry, and we effectively demonstrated and supplied some systems that were automated, underwater vehicle, along with mass spec. And this was from some work that we did, and this is at really deep pressure, 2,000 meters, and they've used it for multiple years. So it just goes to show you that now you've got these systems can actually be out there doing real work. And so that real work gets into spatial observation. And because we have a motion platform that can move, the robot moves through, and modeling networks can be executed. Now you can combine all these things, remote sensing, along with in situ sensing, which is what we do with the mass spec. And then you can get into nowcast and forecast, nowcast being current and forecast being the future and prediction. And that's really what one of the strengths of this, the ability to be able to start doing prediction. If you can start to do the sequence, the flow, and connect these all together, now you're getting the automation of science. And so this is some work I did years ago where we actually did that. We have the mass spec with the mobile robot and being able to do remote processing. I had a circulation model running back landside, and the mass spec on the robot was running around sniffing for chemistry, and the circulation model would direct through wireless where it could go. And so now you've got this ability to be able to actually have all these technologies start to engage and start to have a workflow, as we call workflow. And I was doing this years ago. So this is just an example of starting to connect all these dots together. So I want to do just a sidebar. So in addition to the mass spec, there's an opportunity to bring the lab mass specs or analytical techniques, which is highly automated, into the outside world. And so I developed a series of samplers, and these are meant to not have real-time chemistry, but near real-time chemistry. They can extend the entire chemical biological space. You can capture a sample and then effectively take that sample back in the laboratory after its cartridge is fully loaded, and you can then have that subsequent sample analyzed by the mass specs and the analytical workflows that happen in the laboratory. So these samplers, you know, they're near real time, maybe good enough because you're there, you're persistent, you're enabling the system to be present. So you can have an automated system to be able to act as a sampling, as if you had a human diver, and you eventually got your sample and you're able to create a workflow into the automation of the laboratory. Now we're expanding the automation loop all the way from source to end up detected, from the analytical world, you're getting your conclusions coming in the laboratory. So you go from in the field to all the way into the data that comes out of these machines landside. So I developed these what I call humanoid sampling robots. They do all the function a human does in a laboratory, but it does it in a can. And effectively, we're bringing the human capacity for being able to process samples and bringing that and inserting it into the ocean. So as I was saying in the last slide, now you have an opportunity to have this sample process capture the sample, and then after enough time, enough samples are run, then you can bring that back home. Um, and in the lab, you have the mass spec and the analytical techniques that exist there. And now you have a fully automated workflow. I call this a chemical technician in a can or a graduate student in a can. So this system is more than just a sampler. It can function as what I call a sampler prep system. I won't go into it, but just goes to show you it's got humanoid-like capability. It's flexible. And it can link things, it can process samples, it can capture them. So combining all this, you have a mobile platform. You can run a mass spec with it, or you could put it on a sampler and then couple the field to the laboratory so that you can create a chemical surveyor. And so this is a solar vehicle running the sampling system around and doing sampling. So it's a robotic ship with a robotic deckhand, you know, on board. So in summary, then, this slide shows that we develop a process flow to link mobility, robotic mobility, and sampling and lab-based mass specs, and also link with an onboard. You can link also with an onboard in situ mass spec for real-time screening. So you can go either one channel, which is to do sampling into the lab and using automation, or using full automation, but they both end up focusing on providing high content information, and visualizations and deeper knowledge. And this is the power of automation. And this is where we now have a workflow that becomes truly a foundational area of linking automation mobility, automation sampling processing with all lab analytics, which generally is automated anymore in the laboratory. So this is just real data coming off of these systems. We use that sampling system, the robotic system. So you got the robot along with the robot deckhand, if you would, and then that ultimately goes in the automated laboratory mass specs, and so you got that whole workflow. Just want to show that we actually able to get real analytical grade detection, so that this does work. And this is just a process standard through the sampler system. We achieve comparable signals and very good recoveries. There's more analytical work can be done, and it shows a good proof of this concept. That's good, clean data. So this is a very powerful technique. So this just shows you different samples. These are real world oil samples in seawater, and but I just want to show that this has that automated workflow from being automated running in the water and processing automated in the water to ultimately then having those samples being able to be hosted on automated mass spectrometers, which generally more is in the laboratory. And so now you have that continuous workflow. And again, this is where we have the samples going into LCMS, extending the mass range even higher. I won't go into it, but there's just chemistries that we're able to get with the analytical techniques in the laboratory now that you're sampling. And it's just really a powerful technique. So this is hydrocarbons in water. It's a great, nice solid example. This is real world examples of what's in the water. And that's, detecting it on GCMS, or gas chromatography mass spectrometry, but it's been sampled by robot and by automated sampler. So in the laboratory, again, the mass spec's automated, so you have a real contiguous workflow. Additional sampling of oil spill samples from water from this approach. Fingerprinting is possible. You can then also possible is concurrent biological sampling media, which can be loaded in the system. That's what you see in the upper right. And then you can use both genetic analysis, which is typically done in a lab, and of course electron microscopy. And so you've got, which is another vacuum technique. So you've got all these techniques now can be coupled into this automated workflow. So where I'm going with this is then being able to take the sampling and capture the spatial and temporal dynamics of the chemistry in the water, and then be able to measure it on a 21 Tesla Fourier transform mass spec at Florida State University. So just that's a huge system that's about the size of a room. It's not going into the ocean like the other mass specs I developed, but it just shows you now you can bring in that automation and get into the type of mass specs or chemistry or analytics that won't be able to get into the ocean anytime soon, if ever. This just goes to show we do work ultimately on the data side. So you've got analytical capabilities working from the field, automated into the laboratory, automated, and then the data comes out and they go into automated visualization. And so we have versions of this. So now we're taking it, you're going from sampling the atoms into making the bits and information. And the information then flows into there's mass spec data, and then there's optical data to the lower left. You then bring it into these portals, which has all been developed by us. And so you've got all this data that can be tuned and be able to start to explore into different realms. I'm going to quickly switch streams just a little bit. There's some other stuff we've worked on, which is then these smart reef technologies. And those are a fusion of flexible lights. And then you have scaffolding systems and being able to use these string structures, which lights ultimately are on strings. And now you can start to create new capabilities. And that's something we're working on right now. So I want to highlight that. There are many reasons why we're doing this, but ultimately this reef work really is a new breed of technology, and these are robotic systems. These reefs, these automated systems act as literally smart systems underwater. And now you have the ability to sense and communicate, create networks, and ultimately have the intelligence layered into the environment. This just goes to show you the skeletal system for the architecture for the reefs. You can have different skeleton systems and have different string structures. Those optical sensors that I talk about are all along the string. So this is just, I think, an interesting technology. So the innovations on this are many, but ultimately we're really looking at creating these intelligent systems that are ocean optoelectronic systems for sensing and communication, which you can generate whole layers of sensing and networks that then layer on into the other things. And so you have another layer of intelligence and experimentation to work with. And I just want to highlight stuff that we've done before, continue to do. This is on communication networks. We do all the Internet of Things where you have sensors, communicators, and then you layer them all together and you get ubiquitous communications. So this shows that there's even additional capability from these reef structures into larger networks. So, and then going upstream, let's shift quickly upstream into upstream robotics that can help make the robots as finished systems. We have also developed novel robotics for enabling the subsystems. We have um, so the robots to be able to make robots. And I'll just leave it at that for the sake of time. Just just show some of the features that are made, and this is proven, and we've used this for a couple of years now. So yeah, this is our ability to have robots starting to enable robots. So this shows you that this is related to the robotic system. It actually has its own intelligence. So you have intelligent systems making the robots to then go out in the field to be able to do robotics and to create the data and have the data ultimately being used for machine learning and techniques associated with that. So you really have an end-to-end flow here. And ultimately, and we're doing this right now, using it for demonstrating a small and networked UUV. And so that's where you've got the robot enabling the capability of being able to deploy a lot smaller UUVs, and you get um, more capability. This is a proposed cell for robots, building robots. This slide was made by Hope. Thank you, Hope. But this gets at the automated everything. So this is, I think, my last slide of my work. This is some sequence we did in 2014. We used Twitter as a human machine interface and had real-time data communications back to subscribers. We used threshold limits to the time. At the time, the artificial neural networks, in other words, the AI and compute that we did was not as well developed as today, but the basic process was laid on out. We had a bunch of subscribers, and you can ultimately do really interesting things on this using this approach. And we're starting to do that again because the compute layer is 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 quite substantial. And so now you've got this is on the data side, you've got ways to be able to use the machine learning and the automation to be able to actually help refine the output from this whole system. So you've got robots manufacturing, robots to deploy, robotic data analysis. You have that whole workflow I mentioned some time ago. So it's tempting to summarize the benefits of speed when it comes to this, but that undersells what's really happening. The real gain is coverage. Automated systems explore regions humans never prioritize because they don't look promising. They document failure paths that we normally abandon and forget. And they reduce a very subtle bias, narrative comfort. So humans favor, experiments that fit a story we already believe. Machines don't. This is where democratization comes in, not because everyone gets a robot, because knowledge becomes embedded in systems rather than locked in individuals. Expertise stops decaying when people leave. Furthermore, unsupervised machine learning allows machines to reject and filter out data and explore new frontiers as scientists are doing at CERN right now. The machine is tied into the detection sensor instrumentation flow and rejects most of the data, which is seen as supporting existing paradigms. In this new role, the machine is looking for patterns and anomalies in the signal that could lead to new theories and help break out physics from its crisis right now, many theories, but lack of credible evidence. Stay tuned, because to me, this is leading a leading example of how new automation and science work. And we can then start to take our end up workflow from, robots making things to robots deploying them to then the robotic automation and the science and the data science. And you will see more from what we're doing, starting to bring that link all together. Not much different than the CERN folks are doing on their end. Now, if I stood here and pretended this was all upside, you'd be right now, but trust me, automation creates this paradox. Systems that are perfectly reproducible but increasingly opaque. A machine can repeat an experiment flawlessly while being unable to explain why it chose to run it. Bias doesn't disappear, it moves upstream into objectives, constraints, and data selection. And the workforce issue is real, not because scientists disappear, but because the center of expertise moves faster than institutions. The risk isn't automation, the risk is automation without reflection. So this slide's, on the ethics and the epistemological questions. This is where the conversation gets uncomfortable a little bit and interesting. If a machine discovers something no human anticipate, who's the author? If an automated system proposes a result we can't explain, is that knowledge or is it just poor performance or great performance beyond our comprehension? Historically, the science ties discovery and understanding together in the same mind. That coupling is breaking. We are starting to enter a world where discovery may precede explanation by a long margin. The ethical challenge isn't whether machines are allowed to discover, that's already happening. Challenge is deciding what we expect or accept as knowledge and who bears responsibility when the systems mislead us. So what does the future scientist look like? This is a point where I'd want to remove some anxiety from the room. Automation does not eliminate scientists. It changes where judgment lies. The future scientist is less a hypothesis generator, sorry about that, and a more system designer, something I always consider myself for the last 30 years. You define objectives, you set constraints, you decide what counts as success and what kind of success is unacceptable. Interpretation becomes a human strong point. Meaning, ethics, purpose, those don't automate themselves. This is not a demotion, it's a specialization. So this is my last slide. So here's the core claim I'll leave you with. The automation of science is not about replacing human curiosity. It's about freeing curiosity from being the bottleneck. Machines explore continuously. Humans decide what exploration means. The danger is not discovering too fast. It's really discovering without wisdom. And the opportunity is not speed, but breadth. Seeing what was always there, but never fully examined. Question this paradigm forces on us isn't technological, it's moral. What kinds of knowledge do we really want systems to help us create? So that's the end of my talk, and I can take any questions anyone has. Thank you.